Today we're going to be talking about radioactive decay. This lesson will cover radioactive decay, parent and daughter isotopes, alpha, beta, and gamma decay, and half-lives. Radioactive decay is what happens when a nucleus emits some particles and transforms itself into something different. The nucleus before the particles are emitted and it decays is called the parent isotope, and the nucleus after the decay is called the daughter isotope. There are three different kinds of radioactive decay we'll be looking at: alpha decay, beta decay, and gamma decay. Each kind of decay has a Greek letter that goes with it: alpha, beta, and gamma. In alpha decay, the nucleus emits an alpha particle. Let's look at an example with a radium-226 nucleus. The radium nucleus emits an alpha particle and becomes a radon-222 nucleus. Let's look closer at this to see how it changes. The isotope notation for the radium nucleus shows us that there are 226 nucleons, so the atomic mass number is 226. And the atomic number is 88, so there are 88 protons. For the alpha particle, we can see that it's actually a helium-4 nucleus, that's what an alpha particle is, with 2 neutrons and 2 protons, so a total of 4 nucleons. And the radon nucleus has 222 nucleons and an atomic number of 86. When the original radium nucleus releases 2 neutrons and 2 protons in the alpha particle, the atomic mass number and the atomic number decrease, so now it's a new element. This is called transmutation, when decay causes an element to turn into a different element. If we look at the chemical equation, we see that radium-226 becomes radon-222 plus an alpha particle. In beta decay, a neutron turns into a proton and it emits an electron and a subatomic particle called an antineutrino. You don't need to worry about what an antineutrino is, just know that it's a subatomic particle emitted during beta decay. In this example, we have a nickel-63 nucleus that emits an antineutrino and an electron that's moving very quickly. That's called a beta particle. When it does that, the nickel nucleus becomes a copper-63 nucleus. Let's look closer at the isotope notation. Nickel-63 has 28 protons. The antineutrino and the beta particle have no protons and no neutrons, so their atomic mass and atomic numbers are 0. And copper-63 has 29 protons. Notice that the nickel and the copper isotopes both have mass numbers of 63, so they have a total of 63 nucleons. If we look at the chemical equation, we see nickel-63 becomes copper-63 plus an electron and an antineutrino. The important thing to notice on this decay is that the neutron in the nickel nucleus became a proton in the copper nucleus. Again, the nickel was transmutated into copper. It became a different element. Gamma decay is when a nucleus gives off some energy in the form of a proton. Our example has a plutonium-240 nucleus that's in a very high energy state, and it gives off a high energy proton called a gamma ray. After it does that, it's still plutonium-240, but at a lower energy state. The isotope notation shows that plutonium-240 has 94 protons. The gamma ray is just a photon, so it has no protons, no neutrons, no mass. And after the gamma ray is given off, the plutonium-240 still has 94 protons and 240 nucleons. it did not transmutate. In gamma decay, the element stays the same in the parent and the daughter isotope. If we look at it in a chemical equation, you can see that the plutonium became the plutonium plus a gamma ray, and it's just at a lower energy. Our last concept is half-lives. A half-life is the time that it takes for half of a sample of an unstable isotope to decay into a more stable isotope. Every different isotope has its own half-life that's constant for that isotope, but it's different for each one. In the animation, we see unstable isotopes shown as the red circles. In the first half-life, you'll see that half of those unstable isotopes decay and become green stable isotopes, and then another half, and then another half, and another half, and so on. If we look at the numbers, in the beginning we have 100% unstable isotope. After one half-life, there's 50% of it remaining because we divided the 100 in half. In the second half-life, we divide the 50% in half, and we have 25% remaining. In the third half-life, we divide the 25% in half, and we have 12.5% of the unstable isotope remaining. And in the fourth half-life, 12.5% is divided in half, and we have only 6.25% of the unstable isotope remaining. And we could go on and on and on and on. And eventually, all of the unstable isotope will have decayed into a more stable isotope. In this lesson on radioactive decay, you learned that radioactive decay occurs when a nucleus gives out particles and transforms itself into something different. We saw that parent isotopes decay into daughter isotopes. We looked at alpha decay, where a nucleus gives off a helium-4 nucleus, also known as an alpha particle. And in beta decay, a neutron turns into a proton and gives off an electron and an antineutrino. We discovered that in alpha decay and beta decay, the parent isotopes turn into different daughter isotopes, so they change into different elements in transmutation. And we saw that in gamma decay, a high-energy nucleus gives off energy in the form of a gamma ray or a high-energy photon, and afterwards it's still the same element and the same isotope, but it's a lower energy state. And last, we saw that half-life is the amount of time it takes for half of a sample of an unstable isotope to decay into a more stable isotope. And we discussed that every isotope has its own half-life.